The formula for continuous compound interest is probably nothing new. We actually most likely saw that in Module 2. You've encountered it in previous courses, I would imagine. However, what we want to talk about now is how we actually derive that formula for continuously compounded interest. So where does it come from? And it turns out it comes from calculus. We're going to have to go back to a limit problem, but starting with the simple interest formula, the compound interest formula, we're going to be able to derive that continuous compound interest formula. So let's start with the formula for simple interest, which is A equals our principal investment plus the principal times some interest rate times some length of time. Factoring out that common value P, this is the same thing as P times 1 plus RT is our simple interest formula. If our interest is compounded n times per year, then this formula changes a little bit. Our total amount becomes that principal interest times 1 plus R over N to the NT to become that compound interest formula. And assuming we invest $100 as our principal amount at an interest rate of 6% for 2 years, then we can calculate the total amount of our investment for different values of n. So for different numbers of times of compounding each year. So we can start off if interest is compounded annually, meaning interest is compounded once per year, then after 2 years, we would have $112.36, or just to be a little bit more exact, 0.3600. If interest is compounded semi-annually, then n would be 2, and we would have 112.5509, so $112.55, but this little fraction of a cent as well, technically. If interest is compounded quarterly, then it's being compounded 4 times a year, which is going to give us a final amount of $112.64.93, so 64 cents, about 65 cents. If interest is compounded monthly, then it's compounded 12 times a year, and our total amount would be $112.7160. So even though we're not seeing huge leaps, we are seeing that as our interest is compounded more times per year, that investment, that amount at the end, is increasing. So if we increase this to weekly compounding, there's about 52 weeks a year. So that final investment would be $112.7419. If it's compounded daily, we have 365 days a year. So that would be $112.7486. And if it was compounded hourly, there are about 8,760 hours in a year. Then that would be $112.7496. So again, as our compounding frequency is increasing, so is that total amount left in our account after 2 years. We're not seeing huge differences here, but we also started off with a relatively small investment. But the more times we compound, the greater that final amount is at the end of the year. So in that table above, n is getting larger and larger, which is the same thing as saying n is approaching infinity. So after hourly, we could look at per minute, per second, or what we could do is get up to continuous compounding. So interest is being compounded continuously every immeasurable instant of every day. So we could start with a compound interest formula and take the limit as n goes to infinity. So that compound interest formula is for n compounding periods per year. And what we want is that value for n to be approaching infinity. So we would take the limit as n goes to infinity of the compound interest formula. So with our properties of limits, this p is just a constant multiple, so we can pull that p out in front of the limit. So that'll become p times the limit as n goes to infinity of 1 plus r over n times nt. Now what we're going to do is multiply this exponent by r over r, which we can do because r over r is just 1, so we're not actually changing that exponent at all. We're multiplying by 1, but multiplying it as r over r. So this is going to become p times the limit as n approaches infinity of 1 plus r over n. And then rewriting this exponent in a specific way, we can rewrite it as n over r times rt. So we're just rearranging the order of the multiplication there. And now we're going to make a substitution. We're going to let s equal r over n. And since n is headed to infinity, we have something over this increasingly larger and larger and larger and larger number. So that means that s is actually headed to 0. So now we can rewrite our limit as p times the limit as s heads to 0 of 1 plus s, which is r over n, raised to the 1 over s power, because we had n over r, so the reciprocal of n over r is r over n, so the reciprocal of s is n over r. So we're taking that limit and then raised to the rt power. So if we look at just this portion, where we start with that limit of 1 plus s raised to the 1 over s power, which is then also raised to the rt power. But if we just look at this inner part, this is actually our precise mathematical definition for the constant e. So the value 2.78, et cetera, is defined by this limit expression. So in place of that, we can substitute in just that constant e, which brings us to that continuously compounded interest formula. Our principal times that constant e raised to the rate times time. So our continuous compounded interest formula is a equals pe to the rt. So probably nothing new. And the good news is this deriving this formula isn't something you'll be asked to do on a homework problem on a test, but it's basically demonstrating the idea that this formula that you've been using in classes, possibly for years, possibly just for a few semesters, is a formula that's actually derived through some calculus applications. So one thing that this limit notation, that these limit concepts let us do, is derive this formula for continuously compounded interest. But once we have that formula, we don't need to go back to this limit derivation. We can just jump to this formula that we have and apply it to some application problems.